We're going to find equations of the normal plane and the osculating plane of the curve x is equal to the natural log of t, y is equal to 2t, z is equal to t squared at the point 0, 2, 1. Let's remind ourselves that the normal vector for the normal plane is the tangent vector r prime of t, and the normal vector for the osculating plane is b of t, which is given by t of t cross n of t. I've included the argument here t for all of these vectors to really emphasize that in order to find these vectors, we're going to need a value of t. What we have is a point, 0, 2, 1. Let's first find t. Since the natural log function is a one-to-one function, there's only one value that makes the natural log equal to 0, and we can conclude right away that t is equal to 1. Now, folks, this is going to be a lot to go through, so we're actually going to go through it together because I don't want to talk through it after I've done it if I send you off to do your work. That said, if you want to go off and do your work and then come back and watch, you're welcome to it. I'm going to start now. R of t is equal to the natural log of t, 2t, t squared, which means that r prime of t is equal to 1 over t, 2t. And it follows that r prime of 1 is then going to be 1, 2, 2. That gives us a direction for the normal plane. We can find the normal plane now. Plane with the direction vector 1, 2, 2, and goes through the point 0, 2, 1. So we're looking at 1 times the quantity of x minus 0, plus 2 times the quantity of y minus 2, plus 2 times the quantity of z minus 1 is equal to 0. That's going to simplify to x plus 2y plus 2z is equal to, let me do this quickly here, -4, -2, equal to 6. There's our normal plane, not so bad. So what was I talking about? Folks, we need the unit tangent vector and the unit normal vector. We have the tangent vector, but we need its magnitude. Now we may be thinking, wait a minute, can't I use r prime of 1? Well, after I find r prime of t and then divide by the magnitude, I need to differentiate t in order to get t prime, and that's for the normal vector. In other words, I need t in terms of the parameter t before I can substitute for a value of the parameter. So t of t is, as you know, r prime of t divided by the magnitude of r prime of t. And so I need the magnitude of r prime of t. We have r prime. Its magnitude is going to be the square root of 1 over t squared plus 4t squared. This is just a little bit tricky, but if you look at it for a moment or two, you might see that this becomes the square root of 1 over t plus 2t, the quantity squared. Square rooting the square, we get 1 over t plus 2t. And because we did square root a square, we need absolute values. Now, this expression we just came up with is about to become something in a denominator. So I'd rather get common denominators and express it as a single fraction. And in order to do that, we're going to end up with 2t squared plus 1 divided by the absolute value of t. So there's our r prime. Putting this together with, that's the magnitude of r prime. Putting this together with r prime, we get that t of t is equal to the absolute value of t divided by 2t squared plus 1, right? So that's the reciprocal of the magnitude of r prime, times the vector r prime, which is 1 over t to 2t. Now, because our t is equal to 1, which is greater than 0, I'm going to go ahead and drop the absolute value at this point. It'll become cumbersome otherwise. I mean, it's going to be cumbersome enough anyway, right? So the unit tangent vector, t of t, is equal to 1 over 2t squared plus 1, 2t over 2t squared plus 1, 2t squared over 2t squared plus 1. Now I went ahead and distributed because I did not relish the prospect of using a product rule for the scalar function multiple out front plus a quotient rule for the whole thing. I didn't want to do that. At this point though, we do need to find t prime of t. We need to differentiate. At this point, I'll ask you to pause the video and come back when you have t prime of t. For the I component of t, we're using the power rule and the chain rule. We end up with negative 4t divided by the quantity of 2t squared plus 1, the quantity squared. For the j component, we use the quotient rule on 2t over 2t squared plus 1. After applying the quotient rule and simplifying, we end up with negative 4t squared plus 2 divided by the quantity of 2t squared plus 1 squared. We likewise need the quotient rule for the k component, 2t squared over 2t squared plus 1. And after applying the quotient rule and simplifying, we get 4t divided by the quantity of 2t squared plus 1 squared. Because we're about to find a magnitude of t prime, I decided to go ahead and factor out the common factor in the denominator of 2t squared plus 1, the quantity squared. So out front of my vector, I have 1 over that quantity. And my vector is actually negative 4t squared plus 2, 4t. Now let's find the magnitude of t prime. Remembering that the magnitude of a vector that has a multiple is the multiple of the magnitude, this 1 over 2t squared plus 1 quantity squared is going to be out front of our magnitude. Our magnitude is going to be 16t squared plus, let's see, that's going to be 16t to the fourth minus 16t squared plus 4. That'll be the square of negative 4t squared plus 2. And plus 16t squared for the k component that we had, 4t. I see that 2 of our 16t squareds are going to subtract out. I also see that we have a factor of, 4 everywhere at least, and so I'm going to pull that out. So we have t prime of t in magnitude is going to be 2 over 2t squared plus 1, the quantity squared, times the square root of 4t to the fourth plus 4t squared plus 1, which factors, look at that. So the magnitude of t prime of t is 2 over 2t squared plus 1, the quantity squared, times, I'm going to go with 2t squared plus 1. It divides out. That is beautiful. So the magnitude of t prime of t is equal to 2 over 2t squared plus 1. All right, now we're ready to write down our normal vector. N of t is, of course, t prime of t divided by the magnitude of t prime of t. Because the magnitude of t prime of t is in the denominator, I'm going to write down its reciprocal, 2t squared plus 1 over 2 times the vector t prime of t. Now where is that? Found it. Oh, gotcha. I was premature in writing the vector. The vector t prime of t has a denominator. It's 1 over 2t squared plus 1, the quantity squared. And then we have our negative 4t squared plus 2, and 4t. Hey, look at that. 2t squared plus 1 is going to divide out again. Furthermore, we have a factor of 2 in a denominator that can cut all of the terms by 2. Maybe this isn't going to be so bad. N of t, after all this, how can I say that? N of t is then equal to 1 over 2t squared plus 1 times the vector negative 2t squared plus 1, 2t. And did you catch my mistake? I sure did myself. I wrote for the I component -4 instead of -4t. So my I component should be -4t, and then after dividing out by 2, I should have a -2t. All right, now why did we do all this stuff again? Remember, we're after the binormal vector at t equals 1, which is going to be the unit tangent vector at t equals 1 crossed with the unit normal vector at t equals 1. And at this point, I'm most certainly going to evaluate at 1 because there's no way I want to put all of these expressions into a cross product. Well, t at 1 is going to be, where's t? Way up here. Since t is equal to 1 over 2t squared plus 1, 2t over 2t squared plus 1, and 2t squared over 2t squared plus 1, with t equals 1, this is going to be 1/3, 2/3, and 2/3. Quick little mental check says that the magnitude of t is 1 as it's supposed to be. N of 1. Well, let's see, I think we have n right above here. N of 1 is going to be 1/3 times -2, -1, 2, which we can of course rewrite as -2/3, -1/3, 2/3. Now folks, it occurs to me we don't actually need b. What do I mean? I mean, we need a vector that's parallel to b. Nobody says that for me to find the osculating plane equation, I have to use a unit vector. So what I'm going to do is, I'm going to clear all the fractions. I'm going to find vectors that are parallel to t and n and cross them. I'm actually going to use 1, 2, 2, and I'm going to cross that with -2, -1, 2. In fact, I'd like for you to do that and then come back when you're done. For the cross product, I get 6, -6, 3. Again, we only need it for a direction, so I'm going to use 2, -2, 1. So our osculating plane is going to have an equation 2 times x minus something plus, nope, minus 2 times y minus something plus 1 times z minus something is equal to 0. I keep saying something, something, something because I forgot what the point was. It's 0, 2, 1. So 2 times the quantity of x minus 0 minus 2 times the quantity of y minus 2 plus 1 times the quantity of z minus 1. Simplifying this, we get 2x minus 2y plus z is equal to, looks like that's going to be 4 minus 1, -3. There's our equation of our osculating plane. Now I know we've been at this for a while. They say your online attention span is 6 minutes, and we just hit the 13-minute mark. But I do want to show you what it is that we've just done. I've graphed our curve in GeoGebra, and you can see here the equation of the curve, natural log of t, 2t, t squared, and you can see the curve here in R3. The normal plane is the one that we came up with an equation x plus 2y plus 2z equals 6. And when I show you that plane, now you can see that that plane is kind of speared by the curve, and where the curve intersects that plane, it does so at a right angle. So that's what the normal plane has for us. The osculating plane is the one with the equation 2x minus 2y plus z equals -3. And what you can see here is that it comes as close as possible to capturing a portion of the curve. Now the curve is in 3 dimensions, and so it's not going to exist in a plane. But as you can see right here, the plane is coming close to capturing the curve at the point P that we're talking about. So these are visuals to show you what it is that we just found.